Welcome to Web Handling. My name is Dave Roysum. I am super excited to continue our discussion of productivity. In the last clip, we showed how to predict productivity using some simple concepts and calculations. In this clip, we will show how to measure productivity on your machine. What is happening may be different or quite different than what could be happening down on your machine. Recall from the last clip how we can calculate ReWinder or R2R converting machine productivity. All we need is simple inputs such as roll length and running speed. These calculations are detailed in Chapter 12 of my first winding book and are the subject of several papers presented by other authors in the 1980s. Even easier yet is a free online app, Winder Productivity Calculator by Abbott Apps. The inputs at the bottom can be entered via text box or as sliders as shown in this example. Various productivity measures are given on the upper right hand, while the upper left shows a pie chart of how the activities are being proportioned on that machine. The process engineer or manager can use this tool to do a what-if study. What if the operator ran a faster speed? What if the roles could be changed out faster with automation? And so on. With these calculations, it would be easy to see that some product situations are more challenging than others. The worst combination is small diameter rolls of thick webs, because that causes the winder to need to change out rolls more frequently. During this event, the instantaneous productivity of the ReWinder or R2R converting machine drops to 0. However, a moment's reflection will cause us to think about several things not included in these idealized calculations. These stochastic or irregular events include such things as slitter changes, upsets, maintenance, and more. So, in the paper industry, one common fudge factor for sizing productivity was to allow 4 hours per day for those common but irregular events. Another wild card is the operators. How proficient and diligent they are can have a profound effect on productivity. With sufficient experience, as the paper industry often has, we know exactly how long something should take. The more important question is, how long does it really take? Here I offer 4 ideas, 3 on this slide and my favorite on the next slide. You could have the operators log their own activities. Some PLCs do this semi-automatically by requiring the operator to select a downtime code whenever the machine hits 0 speed. The problems with this approach are many. First, there may be many things that happen to cause the down, and sorting them out may not be easy. Often, it is a combination of insults, such as poor tension control and a hole in the web, that both contributed to a web break. Second, what happens during the down is not accounted for. Most importantly, the operators may not attribute the cause to their own negligence, when that may indeed be the cause on occasion. A brute force method would be to go down to the machine with a stopwatch and a clipboard. However, it should not be surprising that the operators might speed up or slow down, depending on what answers they want you to get. You could record machine activities with a video camera, but the operators might find that intrusive and offensive. The speed versus time plot is an exceptionally easy to set up and very useful. Merely run the speed readout into a data recorder. This could be a circular paper chart or could be a digital recording. In any case, you will know when things are not going smoothly, such as on the night shift. You will also know how long downtimes actually are and how they are distributed. Unfortunately, while this method is extremely easy and useful, the details of the activities on the machine are still missing. While there are many ways to measure productivity, some were given in my last slide, my favorite of all is what I call time cycles by walking around. It is perhaps the easiest and most descriptive method of all. All you need to do is to carry an index card with you that has headings for the various time cycle elements that would be typical of that machine. On a ReWinder, for example, that would be things like run, change set, change master role, move slitters, maintenance, and so on. When you happen to be near the machine for any reason, merely note what event you first notice by putting a tick mark on the heading of the index card. By carrying this card for a month or by having 4 supervisors carry cards for a week, you will have hundreds of tick marks for various time cycle elements. You simply tally them up as fractions and or make a Pareto diagram. For example, if 50% of the marks are run, then the machine is running half the time. If 12% of the marks are grade change setups, then 12% of the time is spent changing grades, and so on. This simple temporary trial can be quite revealing because you are clocking time cycles without the operators knowing about it. Perhaps the only criticism is that the sampling process is not quite random. You will probably be out at the machine more often when they are having trouble than when things are going smooth. Still, that is revealing, is it not? Once you have the times for each of the time cycle elements, you can plot them on a Pareto diagram, which may give you some insight on how to prioritize your efforts. If, for example, most of the time is spent on run, then you should consider increasing run speed, and so on. It is usually easy to determine many of the options for increasing the total productivity of a line by looking at each time cycle element independently. With further effort, you could put a cost to each option. This might require a request for quote from a machine builder if an upgrade were required. The benefit can also be estimated from plant economics. The final step would be to reorder the Pareto diagram for cost-benefit and implement those options which meet company payback requirements. Advanced time cycle analysis must consider that every time element is not the same as the last. In other words, not deterministic. This variation must be considered in critical situations where productivity sizing needs to be close. For example, upsets evenly spaced may not be a problem, while several upsets occasionally grouped together may cause the ReWinder to slow or even shut down the upstream process. There are 4 states to any manufacturing process element. They are run, blocked, starved, and stopped. Each of these, in turn, can be subdivided. So, a machine might be stopped because of grade changes, planned maintenance, or an unplanned upset. 2 states might need further explanation. To be blocked means that you can run, but the downstream process is full. An example might be a ReWinder not being able to run, but the forklift driver has not showed up to take away the finished rolls yet. To be starved also means that you can run, but some critical element is missing. An example might be a winder being able to run, but they don't have any cores. Being blocked or starved may be a sign of poor planning or poor coordination, and is often a source of opportunity. Lastly, we will consider the buffer size upstream of a ReWinder. In some plants, there is no buffer. The ReWinder must run roll for roll, everything produced by manufacturing. Obviously, the slightest trouble on the ReWinder may slow or shut manufacturing. This reminds me of just-in-time or lean manufacturing, which can be instead just a little bit late manufacturing in some plants. In the paper industry, the buffer between the paper machine and the finishing ReWinder may be 5 to 10 master rolls. Here, upsets at the finishing winder or downstream could last for a few hours without shutting down the paper machine. The biggest buffer I've personally seen is one board paper machine which had 150 master rolls in storage. There are many problems with a large buffer. One of them is the huge cost of large inventories. The other is that when the old master roll is run, the ReWinder may find defects inside. Since that manufacturing was done a long time ago, there is nothing to be done to prevent more defects as might be possible if the ReWinder was running 1-for-1 and then complained immediately to manufacturing. SMED is one of my favorite programs and can be especially useful to improve productivity in a manufacturing or rewinding department. SMED was an industrial engineering strategy devised in the 1950s by a consultant to Toyota. The idea is simple, but profound. Grade changes should be as short as possible. Changeovers can be made more quickly using a combination of prepare, eliminate, parallelize, and speed up. The formal analysis is a time cycle combined with a critical path chart combined with creative brainstorming to see the alternatives. Let us use an example of a maintenance down to illustrate preparation. Before the machine is shut down, we would expect that the mechanic to be out at the machine and that they have the tools, the spare parts, and the work order in their hands. Another example of the complete process is the pit crews changing tires. Here, all 4 tires can be changed in less than 15 seconds. While we as consumers would have trouble changing just 1 tire in 15 minutes. Grade changes will cause a productivity hit on almost any machine. However, they are most especially troublesome for rewinders. The reason is that grade changes on the maker are less frequent. In contrast, the rewinder may make grade changes nearly every set in some worst cases, because changing diameters or cores or slit widths might be needed for short orders. Thus, for example, the winder may change from 3-inch cores to 4-inch cores and then back to 3-inch cores. So just how are priorities set, or how is scheduling done? There are many common strategies. FIFO, or first in, first out, is also known as the queue, such as the line to get into a movie. FILO, or first in, last out, is what some warehouses use if a product does not have a short shelf life. Squeaky wheel might be where big customers get preferential treatment, or when emergency orders are received. In many industries, such as paper, trim loss or decal usage schedule which narrower width finished rolls are run to get the most saleable width from a machine. In the real world, a combination of the above priorities is used. In the real world, scheduling is so complicated that it can often be beyond computer analysis and is thus set by a human scheduler's judgment. Thank you so very much for allowing me to share some complexities in productivity analysis and some solutions to those complexities. In the next clip, we will add the human being into the system, as they can have a huge effect on productivity. See you next time.